Oh, and then I can share screen probably with this. So yeah, how's life? How's it going? You guys doing okay? Yeah. Problem set making sense, hopefully. It's due tonight at 11. Oh, I need to post the Friday problem set. Sorry, I'll do that after class. I think I said there's built-in grace periods on the problem sets. I think like 48 hours in case you have issues uploading or you're just having a bad week or something and you just need some extra time. Okay, so it's officially due. And I do have office hours this afternoon, 2:30 to 4. So you can come talk to, and my office is just down the hall. So, okay. So we were working through this handout last week, and we sort of started getting to the idea of like, what is the row reduction algorithm, right? I thought it might actually be a nice idea to illustrate the algorithm to do this chemistry problem again, but sort of full algorithmically instead of sort of the, you sort of like we're plugging things in other things and solving when you did it. And I mean, the way we're going to do it is in some ways harder, like uglier, but it's something you could program a computer to do, right? Because right now we're like, when we look at equations, we say, oh, that equation's simple. Let's start with that one and do that. And I mean, you could program a computer to look at things that way, but it's nice just to give like just a straightforward procedure that the computer has to do. So let's do this chemistry example one more time. Then we can talk about some generalities and stuff, just some other stuff on this handout, some of the terminology. And then hopefully maybe at the end of class, we'll have time to start the second handout a little bit, this linear combinations of vectors, and maybe even do some group work on that or something. But if not today, then definitely Thursday. We'll be spending a good amount of time doing group work on the next handout. Okay. Okay, so yeah. Okay, let's just set this up again. So in the chemistry example, I'm not going to write out everything again, but like, so this is going to be, oh wait, let me stop. Gotta get used to this whole thing of like stopping the share and restarting the share and everything. Okay, so the row reduction algorithm. Because you already did this, and so you got the answers, but I want to sort of show you kind of like systematically what ends up happening. So let's look at the chemistry example again. So, okay, let's just write these equations down really fast. So the idea was like, we could get an equation for each element, right? So like the carbons, we look at just the carbons, we get, let me just write these down. So we had 7 carbon atoms in that first molecule, and then 7 in the third one after the reaction. Check me with these equations. I'm just going to write these equations down real fast. Then we had hydrogen, which was, maybe you should be telling me. You guys can see the screen better than I can. What should I have on the left? 8x plus y equals it's 2w. Okay. And then what's next? Nitrogen. Y equals 3z. And oxygen. Okay, I'm just relying on you guys. You guys all checking each other. Okay. So the first thing to do is to rewrite this as a system in a really sort of like specified way, right? So I'm also tempted to rename these variables x1, x2, x3, x4, just to be like, I think I'm going to do that actually. Wait, what did I just erase? Did I just erase a z, a y? Oh yeah, everything over here is x1 and x2. And everything over here is x3. I'll make z x3 and w x4. W is x4. Okay. So the first thing I'm going to do is rearrange all this stuff like this. So you could think of it really, if you wanted to be super pedantic, you could write it almost like this, right? Like that. These are going to all be zeros after the, which is sort of sad, but not the biggest deal. Okay. Yeah, okay. And so 8x1 plus x2 plus negative 5x3 plus negative 2x4 equals 0. 0x1 plus 1x2 plus negative 3x3 plus 0x4 equals 0. And 0x1 plus 3x2 plus negative 6x3 plus negative 1x4 equals 0, right? So if I wanted to just really systematize this and write it as like in a way, I could write it this way. Then we could make this into a matrix instead, right? Just because it's easier than, I think you guys all got the point quickly that like, it's nice to just write these numbers instead of is that right? Yeah, okay. And then 0, negative 2, 0, negative 1. Okay, and then I draw this vertical bar. I noticed the textbook doesn't do this, but, and actually it's a little bit of a simple thing just because there's all zeros over here. It's actually a special type of system we're going to talk about called a homogeneous system when there's all zeros after the equal sign. But now we can start this sort of row reduction process, right? And the process again is to look at the top left of the matrix, turn it into a 1. If it's a 0, you might have to swap 2 rows. If it's not 0, you could always scale it to be 1. Or if there's a leading one somewhere else and you just want to do that, you could just swap. There, again, a computer's not going to care that much about fractions or anything. And then try to clear out everything underneath it so that you get all zeros. And then you're trying to make like staircase pattern that we talked about like that. By the way, the word echelon, if you look it up, because it's going to be, we're putting it in what's called echelon form, and this is called the, row reduction algorithm. It's there's this form called echelon form or reduced echelon form. And I Googled the word echelon, and it actually describes as like 2 lines. I think it's a military term, but it's like columns of troops that are lined up like in a staggered way or something. So that's exactly what the staircase looks like. So, okay. So the row reduction process is going to be just like, yeah. I mean, it's funny because I tend to like not want to just write out the entire algorithm in words because it just gets kind of tedious. So let's just do it until we're used to doing it. So one thing we could do is we could scale the first row by 7, right? Scale it down. So I would say let's do R1 to 1/7 R1. And so this is going to be a little bit slightly painful. Again, we're doing this by hand some, and then eventually we're going to tell computers to do it for us once we get the process down. That just scales the first row like that, right? 1. And again, you guys have to keep me honest here with the computations and copying from the previous thing and everything. Okay. Okay, and then, well, you know, these are already zeros right here. So we just want to make this one a 0. Yes. Replace row 3 with row 2, like swap them. Well, then the 8 would be here, right? Yeah, like we're going to want zeros underneath this whole 1 right here. And so you could swap them, but we're still going to have to do the same thing to get rid of this 8 eventually. Right, I see what you're saying. Like you could put the 0 there. And then you're starting at the staircase, but then it's almost like you'd go over here, but then you have to go backwards, which we don't want to go. That makes sense. Yeah, so a lot of this is arbitrary, but it's just like a nice algorithm. So yeah. Okay, so the thing that we do then, the next step we talked about was we taking a row, like row 2, and subtracting 8 times row 1, because that will get rid of this 8 right here, right? We want to get rid of that, make it a 0. So all that changes is row 2. Just actually put in the 3rd and 4th rows. I'm going to copy them. So now when we do the 2nd row minus 8 times the 1st row, you kind of have to do this arithmetic each time, right? Like that's 1 minus 8 times 0. This is minus 5 minus 8 times minus 1, which is minus 5 plus 8. What happens to this? Stays the same, right? There's a 0 there. The nice thing about the last column is it never changes from 0, 0, 0, 0 because they're not interacting at all. Okay. So now what we have is we have the staircase like this, but we want it to go this way. We want it to go that way, right? That's already a 1, which is convenient. And so I want to turn these two things into zeros to keep building the staircase, right? So again, I'll write the steps, but then you guys do the computations and keep me honest. So we're going to take row 3 and just subtract row 2. And we're going to take row 4 and subtract 3 times row 2. Is that right? The first 2 rows stay the same. Hope this works out. We didn't copy something at the beginning. So what happens to the 3rd row? Yeah. Negative 2 or plus negative 0 minus negative 2 is plus 2. 0. Okay. And then what about the 4th row? Someone get the 4th row? You know it's going to start 0, 0. Negative 15. 5. Interesting. 0. Okay, and this is starting to look a little bit interesting to me. So now we have the staircase like this, right? But we want it to go like that. We could scale the first row by negative 6 to make a leading 1 right there. By negative 6, by 1/6, negative 1/6. So let's take one here. I'll do the easy ones. 0, negative 1, 0. We introduce fractions, but that's okay. We're sophisticated mathematicians. We can handle it. 0, 0, 1, negative 1/3. 0, 0, 0, negative 15, 5, 0. No, yeah, question. And then they'll be the same. You're noticing like these two will be the same. It's very true. We could do that. Again, the way the algorithm tends to want to work, the way a computer tends to want to work is scale this non-zero entry to 1, and then just do that process over and over again. See, you're too smart. You already see where this is going. You know what I mean? So if you didn't see where it was going, but right, you could multiply this by negative 2.5 and it would be the same row, and then you know you're going to get row of zeros, which is interesting. So, okay, so I'm just doing the dumb thing. So what are we gonna do next? What's the next step? Add 15 times row 3 to row 4. So row 4 becomes row 4 plus 15 row 3. I promise this course will not be lots of me doing row reductions at the board, but we might have to do it a couple times early in the semester. Okay, so notice, by the way, that like nothing changes. One reason the staircase thing is nice is that this stuff over here doesn't change when we add multiples, and if we scale or swap or add multiples, like these stay 0, which is part of the point. You're not like causing things to interact with each other. And then that's 0, and 5 plus 15 thirds, 5 minus 15 thirds. We get a row of all zeros. Okay, so that's already interesting. In fact, the staircase ended up jumping over. Like we kind of like without a priori, we wouldn't know. Like it might still need to go like this, right? But we ended up getting this extra 0 here. So this is what's called echelon form. And you could do the thing where we translate back to equations and then sort of like back substitute. But what I will say is that you could keep going. I could even make things, I could sort of not do the back substitution step. Instead, every time we got like a leading 1, we cleared out everything below it to make a 0. At this point, we could also clear out things above leading 1s. So we could also make these 2 zeros. Because then you don't have, like, if you think about translating, make these back to equations, right? These would have x3 terms. But if you want to make these equations that you end up with as simple as possible, you could make these 0, these 2 elements 0, and then you wouldn't have any x3s except in that equation. And again, having all zeros over here is good because it doesn't interact with anything in previous columns. That's kind of the point of the algorithm, is like, it's really recursive in the sense that like once we got to this step, we haven't done anything with row 1, right? We're just almost down to like a 3 equations and 3 variables situation. And then at this step, we were like 2 equations and 2 variables situation. But let's actually keep going. And let's just get rid of these. So you're kind of doing the back substitution in the matrix form instead of doing it by hand, instead of translating to equations and doing it. But let's get rid of these. So, but now I'm going to use this leading 1 right here. So I could take row 1 and then I could just add row 3 to it. Right? Because that'll cancel that. Again, these won't change. This will become a 0. And it'll change this, which is maybe annoying, but at least it's going to be something very systematic. And then row 2, we're going to subtract 3 times row 3. I think, right? Okay, so, well, the bottom 2 rows don't change. This stuff doesn't change. And I think we just made both of these zeros. So it's really just what matters what's here, right? So what goes right here? -1/3, we just added those. And then here we took -2 and we subtracted 3 times -1/3. -1. We added 1 basically. Okay, and now this is what's called reduced echelon form. And the way to tell this is that, like, actually, I should just start telling you terminology, because like these positions right here are called pivots. Again, this is just terminology. These are called pivots, because it's kind of how the staircase ends up being made. It's like where the pivots are. So we might have expected a pivot down here in normal circumstances, but we had that things perfectly worked out. You know, like kind of in general, you might expect to get just pivots along the diagonal, but sometimes you don't. In echelon form, the fact that this was 0 is sort of an accident. In echelon form, you have zeros below the pivots. In reduced echelon form, you have zeros everywhere except the pivot number in these columns. So in any, like this is called a pivot column. These are called pivot columns. We're gonna spend a lot of time talking about rows and columns in this class, right? You do the crossword, you could think of cross and down, but rows and columns. And so, right, we're gonna focus on the fact that these are called like pivot columns. And in reduced echelon form, the only non-zero entry in a pivot column is the pivot. You can always clear out everything else, make it all 0. In some ways, this is the simplest we could get when we convert back to equations, which we should do now, and see how to interpret this. Oh, okay, I think that's good enough. All right, so let's just do this. Yeah. So yeah, convert back to equations. Once you have it in reduced echelon form, it's pretty easy to get solutions from there. So we have x1 minus a third x4 equals 0. We have x2 minus x4 equals 0. We have x3 minus the third x4 equals 0. And then really the last one is just 0 equals 0, which is just no information, right? Okay, and so, like I said, again, just terminology type things. These are called the pivot variables now. Because they involve pivots. This is called a free variable. And the reason we call it a free variable is if you think about it, I mean, we can actually get x1, x2, and x3 in terms of x4 now easily, right? And then we can then pick x4 to be whatever we want, and that will determine x1, x2, and x3. So let me just write that down. Okay, hopefully I won't be doing more horrible row reduction today. We do want to understand the algorithm. So, and it's very interesting to see how we get the same answer that you guys had. And I'm tempted here to just write x4 equals x4. Because our solution should be a 4 tuple, x1 through x4, right? And so x4 is free. I.e., we can pick it to be whatever we want. To be whatever we want. And that determines x1, x2, and x3. Or forces, right? That forces x1, x2, x3. In particular, what we're going to do often is we're going to give x4 a name like t or something, like it's a parameter kind of. And then just think all the solutions we can write in terms of this parameter, right? Let's call x4 equal to t, you know, a parameter. And the other thing I might as well start introducing is this idea that we're going to actually write tuples like pairs, triples. This is like a 4 tuple. We're going to actually write them in columns. It's actually a very standard thing in linear algebra. We're going to write vectors in columns. So we could write something like the following. We could write x1, x2, x3, x4 equals, now I'm calling this t, right? So 1/3 t, t, 1/3 t, and t, like that, right? And so that's really a way, this kind of gives you all possible solutions. Set t equal to anything and you get a solution to this, right? So this gives all solutions. By the way, we should say this is infinitely many solutions. And we can sort of represent that like this. This is called, again, I'm just throwing like language at you that we're gonna start using over the course of the semester. So let's just start getting used to it. This is called like a column vector. And basically, so this gives all, this sort of lists all the solutions, all possible solutions. And if you forget about the chemistry, right, we could have any number for t. We could have -34 for t or something like that. So for example, the example I think you guys did, which was kind of an obvious example, is t equals 3, right? Because that leads to the solution 1, 3, 1, 3, which was exactly kind of the like natural chemistry solution you would come to. Cool. So we illustrated the algorithm. We illustrated how we would write down solutions. In this case, we had infinitely many solutions. There are cases, again, we're going to go back to some smaller dimensional cases in a minute, just to sort of think about, can we think our way through all the possibilities? But here, if we hadn't gotten this 0 right here, we could have scaled it to be 1. And then you would actually get a unique solution. Like when you do this whole process, you would end up with like all 1s and all 0s, all 1s on the diagonal, 0s. Here it has all 0s, so actually the only solution would be 0, 0, 0, 0. But I kind of wondered actually in chemistry if you solve a system like this and just get all 0s, does that somehow mean that that's like not a possible chemical reaction or something? I really should ask I know like half the chemistry program, I'm like pretty good friends with like half the chemistry department, I should really ask them. Professor Takamatsu, she triple majored in math, physics, and chemistry at University of Chicago. So she knows a lot of stuff, so I could ask her. Anyways, yeah, she knows stuff. So yeah, I should ask her, because I kind of wondered if this actually had any bearing on like actual chemistry, like, you know, like if it works, does that mean that they do react? If mathematically it works, does that mean they do react? Probably not. But if it doesn't work, then maybe they don't react. Does anybody know things about chemistry? Right. Right. But I'm kind of going backwards and saying, could we discover chemical reactions or rule out chemical reactions if there was no solution? Yeah. Oh, okay. Oh, wow. Okay, so we're going farther into real chemistry. Yeah, right. Probably like this isn't fully predictive of like everything. But that makes, yeah. There's a lot, physical chemistry has a lot of math in it too. Like that's actually very cool stuff, which I wish I knew more about. Anyways, so it's sort of interesting to start to think like what the implications are. But I do sort of wonder if you like, if you had like two molecules and you wanted to see if they could react to make these other two molecules, and you set that up and solve this and you just got 0, 0, 0, 0, if that would mean like, nope, those don't react. So right, you might not be able to say anything positive, but maybe you can say things that are negative.
Well, it would just mean that something's missing.
Oh, you need like a catalyst or something. Ah, interesting. Interesting, okay. See, I'm not a lab scientist, so I'm like, I want to figure out as much as I can without actually using any real world. I just want to like use my brain and a piece of paper and see what I can figure out. Okay, so, all right, anyways, so this sort of shows you, right, so this, sorry, back, let me just pull this back down so it's, at least it's on screen also. This sort of shows you like what all the solutions are. But there's infinitely many of them, okay? So this is the one like nice solution, but you know, you could, I think I said this to people, I think when you guys are working on this in Gather, that like, it also says if you had 10 and 30 of the first molecule, that would create 10 and 30 of the reaction molecule, right? So like, you can scale these up, which makes sense. You just have more of each thing. But they need to be in these ratios. So, okay. Let's go back and talk a little bit about the possibilities and when you have like lower dimensions. So I just want to like think about some of these questions, especially the 2 equations and 2 variable case. Because one thing, and this comes up on some of the homework problems, those ones that have like letters in them, like H's and K's and stuff, that it's worth thinking about. That we're thinking of these as just equations and this process will solve them, right? And you can apply this process to those homework problems and tell you something. Yeah, but okay, let's talk about the 2 equations and 2 variables, because I think that'll illustrate a lot of the general stuff. And then we can maybe talk about 3 equations and 3 variables also. Because you can do this process, but when we see it 2 equations and 2 variables, we can also interpret them as lines in the plane, right? And think about whether those are lines that are intersect or don't. And I think that's very illuminating. So we might as well take that approach and look at things that way. So let's think about the general 2 equations and 2 variables. So yeah, let's go back. 2 equations and 2 variables. So I think I wrote that in general on the handout as ax plus by equals r, cx plus dy equals s. But rather than solve, like you can really go and try to solve these explicitly, but I just want to think about possibilities. Like think of these as lines in the plane, right? Think of these as lines, plane. Then what sort of possibilities do we have? Well, let's just think of this as like, let's call this L1 and this L2 or something like that for a line. So we could have L1 and L2 like this, right? In this case, if you solve the system, what's going to happen? Yeah. Yeah, you're going to find this point here, which is the 1 intersection point. Good. So in this case, one unique solution. I guess I want to say these are like possibilities. Possibilities. Okay, and what other kind of situations could we have? So this is possibility 1. What else could happen? Yeah. The 2 lines could be parallel, right? L1, L2, so that would be no solutions. And we should give an example of this, right? So let's just say, like, for example, you could have x plus 2y equals 3, and x plus 2y equals 4 would be like a simple example like that, right? Where these are clearly parallel. And clearly are different lines. So you'd have no solutions. It can be slightly more disguised if you have this multiplied by something. Like if I had 3x plus 6y equals 12 or something like that. And then what's the third possibility? Yeah. Same line. It could be the same line just disguised, right? Like L1 and L2. So this has infinitely many solutions because everything. So for example, you could have x plus 2y equals 3, but you could have 3x plus 6y equals 9 or something like that, right? And that would be the possibility. So we have 0, 1, or infinitely many solutions. But we could also think about what the echelon form and the reduced echelon form would look like in this case, like in each of these cases. So like, I sort of plan this poorly now because I don't have the right space on the board. But like, if you think about what would happen, what would the reduced echelon form look like? You know, if I start with whatever the numbers are and I have two different lines that are not parallel. So we're gonna scale this to 1. We're gonna make this a 0 underneath. So there's a pivot there. There's always a pivot. Like you can always find a pivot in the first. What's gonna happen here? Am I gonna have a pivot here or not? I'm gonna have a pivot, right? Because I'm gonna want to like, and then I'm gonna clear out that and make that a 0. I'm gonna want a unique solution. And so the book does stuff like this. And I kind of like to have like, this is kind of a general thing, a generic thing where we use asterisks. But it's like, it should reduce to that. Whatever we start with should reduce to this, and we get one unique solution. Now we just say x1 equals and x2 equals, or x equals and y equals, right? Does that make sense? The book also talks about just echelon forms, like possible echelon forms. Let me just put this down here with this, sorry. This is kind of ugly, but we could also just have, maybe this is also very non-controversial. The book does things like this. It writes like a square for like where a pivot is. And then that could be anything, and then that could be anything, and that could be, so this is like, because you could do sort of what Mariusz was suggesting before of like not actually scaling to be 1 and just scaling and making things go away. And then like not scale all the leading coefficients to 1. So yeah, this is a way like, this is a pivot non-zero. And this is anything. Could be 0, could be non-zero. Like these could both be 0 because it could intersect at the origin, the two lines, you know. So you'll see, I just think it's worth mentioning because you'll see, I kind of like this, like you could sort of try to think about all the possibilities. But once you have the echelon form, you can kind of go back and forth between the echelon and the reduced echelon forms. Yeah. Okay, so what about in the second case? I really wish I had notability and I could like copy and just move things or like circle things and move them around. Because my board work is pretty terrible right here. But yeah, what about, you're gonna say, and then non-zero, yeah, because, right, I mean, if you think about this, we're gonna have, like, when we clear out the x below the x, we're gonna get a 0, but we're also gonna get a 0 here. But then, so here we would just subtract the 2, and so we would actually get a non-zero there. So, sorry, let me do this. So the reduced, I think actually they use like REF for reduced echelon form. would be zeros here. This could be anything. This could be anything. This is not 0. You could scale this row to be 1 if it's not 0. So we could write this like this. I mean, maybe the echelon form is more natural, which is like pivot here, zeros here. And actually, oh, I guess I can make that a 0 actually too by clearing out the 0 above the 1. But this actually, the book calls this a pivot. Like there's sort of a question of whether you want to consider the stuff after the equal sign like a pivot. But that's sort of, if I interpret these symbols the same way as I'm doing here, which is like non-zero, that being a non-zero number. And so this is what a system with no solutions would look like, because this translates to 0 equals non-zero, which is a contradiction. Whereas here, these both just translate to x1 equals and x2 equals unique. Does that make sense? Okay. Sorry again for the shoddy board work. But then, now what about the third case? What's the difference? What's the, yeah. All zeros on the bottom row, good. So this is this one, this we can't control, it could be whatever number happens to be, whatever the ratio is of these two numbers. This is all zeros, and that this is also something we can't control necessarily. So we can get that. Or, and then in echelon form, it would just be pivot. I mean, it's sort of the same thing. Right. And then the thing that's worth mentioning is we have a pivot variable and a free variable in this case. I mean, I guess there's like a free variable here, but because of the 0 equals 1, that means, or 0 equals non-zero, that means there's no solutions. So, but here, because there's solutions and because there's a free variable, that means there's infinitely many solutions, right? And this is sort of what we got in the previous chemistry example. Also, we got something that looked like this. It was just a 4x4 with an augmented column. So yeah, this is a pivot column. This is a free column. And then we do have infinitely many solutions. Okay. So it's kind of nice. It goes with the geometry. Yeah. Any questions about any of that? So if you look at the handout, like number 7 is kind of like, we've kind of examined this whole case. We haven't solved the general 2x2. I think one of the groups did it in group work last week, but we could talk about that at some point. Okay. Two equations and 3 variables, 3 equations and 2 variables is sort of interesting. 3 equations and 2 variables. Maybe we can think about that a little bit together, like, because now you have 3 lines in the plane, right? And those can intersect in interesting different ways. So maybe yeah, let's just start with like maybe I'll let you guys do it just at your chairs with like your neighbors, just to try to think through possibilities. Because it's sort of a fun thing to try to think through what all the possible reduced echelon forms are in a given situation. I mean, that's my idea of fun. Maybe not for you. But yeah, if we did 2 equations and 3 variables, so we'd have like ax1 plus bx2 equals r, cx1 plus dx2 equals s, and ex1 plus fx2 equals t. So this could be 3 lines in the plane. So think about the kind of staircase patterns you could make now. Yeah, go. It is. I wrote that wrong. Thank you. Yes. Perfect. 3 equations and 2 variables. So, you know, you're going to start with, I mean, you're going to think about where the pivots can be, right? There's always a pivot in the top left. I think we're always assuming that these are not all 0, like that the variable x1 matters. So there's no like 0, 0, 0. So we can always put a non-zero thing up here. And then it's like, well, what can happen? You know, like, I mean, how many different, we came up with 3 different reduced echelon forms for the 2x2 case. If we're gonna always have the staircase pattern, how many different scenarios can we come up with in the 3 equations and 2 variables case? And how does that correspond to all the different scenarios you could have with 3 lines in the plane, right? It's a little bit of an open-ended question, but turn to someone next to you and say hi, introduce yourself. Can be in groups of 3 if you want. So I want you to try to like think about this with those people that you're now talking to. Think about the possibilities. You could try to think geometrically, and then what the corresponding reduced echelon form would be. You could try to think about like just the process of row reduction and how that would create different forms. But let's just see how many we can come up with, like different reduced echelon forms. Can we do that? Talk it out with people. Try to write some stuff down. I'll wander around and hover over you. Maybe I'll pause the recording for a couple minutes. Okay, so I gave you a few minutes to think about that. Who has ideas? Who wants to tell me an example of either a geometric or situation or an echelon form? Or did you have a certain number? Did people come up with a number? How many echelon forms are? 5 different. You thought of 8 configurations of 3 lines, but you came up with, but in terms of echelon forms or reduced echelon forms, there's led to 5 different. Oh, you didn't say that there. You were just focusing on the geometric stuff. But then I saw you nodding when they said 5. I don't know if that was. You have 5 different echelon forms, or 5 different geometric configurations, or oh, okay. Yeah. What about you guys? You have 6 different geometric. Okay. You had 6 geometric ones. So let's think about, okay, so if we have 3 lines in the plane, I'm sort of curious about, so someone tell me one. Tell me a configuration. Yeah.
Like there would be 3 solutions, so like kind of like a taxonomy.
Oh, like a triangle kind of? So there's really no solutions because there's no one point that belongs to all 3. Like I see what you're saying, like they intersect in those 3 points, but like there wouldn't be one pair that would solve all 3 simultaneously. So this would be, that would be yeah, so this would be a no solution case. What else? Other examples? Yeah. All going through the same point. So that's a unique solution. Okay. What else? Yeah. So 3 different parallel lines. No solutions. What else? All the same line. Maybe I'll just do ×3 like that to be like all the same line. Oh, interesting. So that's one, and then you said you could have ×2 there, like the same line twice. That's 6. Yeah. Oh, I don't think we've seen that yet. Wait, so I guess I should have been writing like number of solutions here was no solutions here, 1 solution here, no solutions here, infinitely many solutions here, no solutions here, no solutions here. Sorry, you said doubled line, and then one that crosses it. So that would be, would that be 1 solution also? 1 solution. Anything else? Oh, you guys had 8. We had 3 separate parallel there. All through the same line as there. No, I don't know. Was there an 8? Maybe that's it. Oh yeah. In the echelon form.
Like, I mean, you might have like zeros instead.
Well, okay, yeah. So there's an interesting thing about like, what does it mean to see that a system has no solutions, but whether or not there's different echelon forms is sort of interesting, right? So, okay, I didn't actually think about the geometric cases, so I don't know if we're missing one or not, but it seems reasonable. There's nothing obvious to me that we're missing, but okay. So now let's think about the echelon forms. So, and I think of this, you can almost do like a flow chart. So I'm assuming that no column is 0, because if you allow 0 column, there's more possibilities. Again, I'm sort of assuming that like these variables each matter. If you have a column of zeros, once you go over to here, then it's like the x1 variable is just not even relevant. I mean, that could happen with lines. You could have all like horizontal lines or something, and then the x1 variable wouldn't matter. But for this case of this, I'm just going to assume no 0 columns. So that was sort of the geometric interpretation. But let's think about so for example, that means that we could definitely do this, right? We can definitely make a pivot there and clear out everything underneath. Now this is not echelon form or reduced echelon form yet. I'm just saying this is like a starting point, right? So you have a pivot in the first column for sure. And now either you have, so this is like, yeah, pivot in first column. And now, so we have this part of the staircase. So now that staircase, if it's we could either there's a pivot here. I mean, this could be 0 right here, but we could swap it and make that, if that's non-zero, right? We could swap it. So there either is a pivot in the second column or there's not. So I'm just gonna think about this like a flow chart. Pivot in second column, question mark, let's say yes, no. So if there's a pivot in the second column, we could always swap, so we can definitely make this a 0, right? We can clear the 0 out below that. If the 0 was here, we could swap. And so now we're at this point. Or if we're over here and there isn't a pivot in the second column, then that sort of means that we actually cleared out zeros here inadvertently or something. Right? I'm just trying to think this through logically, basically what could happen when you're row reducing. Okay, now then there's possibilities there's possibilities here. What are the two possibilities here for this like bottom right entry? Yeah, if it's 0, then that's good actually. You get a consistent system. If it's not 0, then there's a pivot there and you get an inconsistent system. So I guess this leads to that, or yeah, I'm almost just like thinking what could happen when I do these numbers. So that's like that, right? Those are those two possibilities. Now what about, because it's kind of like we're just saying the third column. Is there a pivot in the third column or not? Now what about here? What could happen with these two asterisks? Yeah. Yeah, please. Yeah. That's right. Any non-zero number. Yeah, this little square I'm using as a non-zero. I think I put on the board somewhere. Yeah, question, please.
I guess one thing, I feel like from step the two actions that we set 0, those can also be the same.
They could both be pivots. Well, if they're, I think if they're both, yeah. But if they're the same, then you could sort of get rid of one and make it 0. You know what I mean?
Oh,
Or yeah. Or they could, so if they're both, if either one of them is non-zero, if either or both of them are non-zero, you can get to this case because you can put a non-zero number here and then make this 0. May already be 0. Or they're both 0 and then you end up in that case. Is that fair? Yeah, well, oh, this one? Well, we haven't said yet. So because we haven't decided what these numbers are yet. So here you're right. This is no solution. This is a unique solution, right? Because we could, that we know that this equals, and then we can back substitute that. And now we have a couple cases here. Sorry, again with the board. So what could happen? So run out of room on I. What am I doing? Okay. So what could happen? What happened with these two asterisks? They could be, yeah, they could both be 0. They could both be non-zero. One could be 0. One could be non-zero. What if they're, what are the cases? So what's an interesting case? If they're both 0, they both have to be 0. Then what is this? It's really 3 of the same line, right? And it's actually infinitely many solutions. And okay, let's see, how can I find room for this last case? Sorry, if you're in your notes, you can just put this down here. So if either of them is non-zero, if either of these two asterisks is non-zero, then that's bad, right? So if they're both, so you could basically say like pivot here, and then you can again make that 0 by clearing it out. But you can sort of always make the third equation. Well, you can't always make it all zeros, but if, yeah, no, sorry, you can't always make it all zeros. But and so is that, how many solutions is that? None. So that's also no solutions. Okay. Actually, what I'm going to do, I think, is, so we have 4 different echelon forms. I might write the corresponding reduced echelon form, and then let's see if we can identify which of these cases go with which. Yeah, question.
the two in the last column are both pivots, not matter.
You mean like non-zero numbers here and here? Well, so you can guarantee that there's at most one pivot per column because I could always use this non-zero number to make this zero. Like you know what I mean? Like I could subtract and make it go away. So that's why I put a 0 right there. Yeah, like if you notice in all these ways, there's only ever one square per column at most, you know. Okay, let me rewrite these and then. So we got four potential echelon forms. And I'm just kind of curious if we can associate each of these pictures with one of them. So summarize. So let's see, we had, I think the unique solution case is sort of nice. So we have this. Which we could do in reduced echelon form. We could scale this pivot to 1. We could scale that pivot to 1 and clear out that asterisk above it. So 1, 0, 0, 0, 1, 0. And then these are still not controlled numbers. They can be whatever, depending on the situation. Maybe I'll just say like, that's like echelon form to reduced echelon form. Could actually be making a table or something. Yeah, actually, can I make this as like a table? Sorry. Here we have a table. Okay, this is echelon. This is echelon form. This is reduced echelon form, and this is geometry. This isn't necessarily what this class is about, like trying to, but I just think it's kind of a fun exercise and sort of starts to illustrate the possibilities. So we have that. Again, I can just copy. Oh, I guess I should say number of solutions. Actually, column 2, right? Number of solutions. And then geometry. Okay, so this was one solution. We had the case of 2 pivots, but no solution. Which we could reduce to 1, 0, 0, 0, 1, 0. We could even reduce this to 0, 0, 1 right there. It seems sort of silly at that point, but you could scale this to 1 and then clear out those and make that 0. Kind of silly, but if you wanted to leave these as asterisks, I wouldn't blame you. We had the 1 pivot. And consistent, right? And that just changes. All we can do there is scale the pivot to be 1. And then we have the 1 pivot inconsistent. Hopefully my squares and my zeros look different enough to you. And what we could do there is turn that into a 1. Make that a 0. Okay, so sorry, I'm just trying to recap what we had. This was no solutions, this was infinitely many solutions, and this was no solutions. Okay, so really I was just doing this all so that we could try to see which geometric things go with which. So the easier one is this one. What picture goes with this? Number 2, the 3 lines going through 1 point. Okay, that's good. Now, what about picture 1? The sort of the 3 lines, none of which are parallel. What do you think is going to happen there when you do real reduction? You think you'll get 2 pivots or 1 pivot? Yeah, 2. Yeah, it's almost like if you just forgot about the third equation completely, you would just have 2 lines that would intersect. So those should reduce down to like sort of this case with 2 pivots, right? So we have the, like I should do these in color or something. So we had this one here. We have this case. What about 3? The 3 parallel lines. That'd be 1 pivot or 2 pivots? Yeah, 1, because you'd have the same sort of ratio, right? Like you'd have to have like they have the same slope, so you'd have the same ratio of like the x coefficient to y coefficient. So when you clear it out, you just get 1 pivot. So that would be that. I think there's more cases for these, so I'll put commas there. What about 4? I guess 4 is kind of obvious. Yeah, it's the only place, right? It's 3. What about 5? Could be kind of hard. 2 parallel, 1 not. Yeah. Exactly. Forget one of the parallel lines. So there should be 2 pivots. Good. So that shows up in the 5 case, or that shows up in that case. What about 6? Also, what's going to be here or here? They're all parallel, so this feels like the all parallel cases, right? That's right. Yeah, so there better only be 1 pivot because that could happen. So we could have that. And then what about the 7th case? Your logic is good for that, right? Like if you forget one of the parallel lines, you'd have 2 non-parallel lines. So good. Wow. Okay, we've gotten all the, we've done it all. So no, wait, that's not right. Yeah, I just totally messed up. There would be 1 solution. It'd be interesting to see how that would actually happen, but right, I guess there should be 2 pivots, but it better not be inconsistent. I mean, certainly logically, this better be. Yeah, okay. So I think we've gotten them all. It's sort of fun to think about. These are these are called consistent and these are called inconsistent. The twins with 0 solutions are called inconsistent. Yeah. Okay, that was fun. It's kind of interesting exercise. Since we're almost out of time, let me just look at the screen and think about what we want to talk about. So, right, I mean, we sort of talked about some of this stuff like reduced echelon form. We talked about 3 equations and 2 variables. You can think about 2 equations and 3 variables, which is like 2 planes in space. Different ways those can intersect. Could you ever have a unique solution in that case? 2 planes in space. What's that? Yeah, if they intersect, there's going to be a line of intersection, right? So you'd have either have infinitely many solutions or no solutions. That's pretty much it. Which is sort of 2 cases. Well, I guess you'd have the parallel or the same, 2 parallel different planes or the same plane. So you could have 2 different ways to get infinitely many solutions, either a line of solutions or a whole plane of solutions. So you could try to do that to think about what are the possible. I think there might be homework questions related to this actually. In fact, I hope this isn't on the homework. Well, I can change it because I haven't posted it yet. But I think homework for Friday. Yeah, so this is sort of the introduction. We sort of know what row reduction is now. We know what matrices are. There's these word pivots and stuff. We'll come back to this because there's different interpretations. And then the big thing will be, we're going to move on to this linear combinations of vector. Wait, what did I just do? No. Yeah, okay. So we're going to move on to this next handout. And it's really section 1.3 of the book also. And what we're doing, if in some ways what we've been doing is we've been looking at matrices and we've been looking at the rows as equations, and then we're solving equations and variables. We're going to shift perspective and look at the columns. And we're going to think of like each of these, as a column vector. And then there's this question of like, could I write the third column as a combination of the first two columns in some way? So we'll do some examples on Thursday and get into that. And we'll definitely do some group work. I'll make you go to the boards. So cool. Should we call it a day? Those classes that go to 1:05, it's always like, once you get to 1 o'clock, it just feels like lunchtime. So, all right, cool. And like I said, I have office hours 90 minutes from now. And I'm on email and stuff. So have a good one.